So this is a very the different kind of learning than what we looked at in ML, right? So so in machine learning, we looked at familiar modes of machine learning where the idea was to learn from data. So you had given a lot of data as training instances for you, and essentially you were trying to learn from those training instances as to what to do, right? And there were different kinds of problems that we are looking at. So one was supervised learning problem, in which we were looking at classification and regression. So in the machine learning class, we looked at learning from data, right, primarily. So one of the models we looked at was supervised learning, right, where we learned about classification and regression. The goal there was to learn a mapping from an input space to a output, which could be a categorical output, in which case it's classification. It could be a continuous output, in which case it was called regression, right. So if you haven't been in the ML class, don't worry about it, right, because this is just to tell you that RL is not whatever you learnt in the ML class, okay. So if you haven't learnt anything in the ML class, then you don't have anything to unlearn, so don't worry. So the second kind of learning thing we looked at was unsupervised learning, where there was really no output that was expected of you, right. Since therefore there was no supervision, the goal was to find patterns in the input data. I'll give you a lot of data points. You can find out if there are groupings of similar kinds of data points. Can I divide them into segments, right? So that kind of a thing was called clustering, right? Or you were asked to figure out if there were frequently repeating patterns in the data, right? And so this is called frequent pattern mining, or derived problem. There was association rule mining, and so on and so forth, right? So people have heard me give this analogy multiple times before, but this is the most apt one. How did you learn to cycle? Right? So was it supervised learning? Yeah, okay. How did you learn to cycle? Did somebody tell you how to cycle and then you just followed their instruction? Okay, first of all, do you know how to cycle? Yes? Do you know how to cycle? Yeah, you? Yes, okay. How did you learn to cycle? Fell down a couple of times, and that automatically made you cycle. You have to actually figure out how to not to fall down, right? So falling down alone is not enough, but you have to try different things, right? It's not supervised learning, right? It's really not supervised learning, how much ever you think. Because now that I have given this talk multiple times, people are getting wise to it, right? Earlier when I used to ask this, people used to say, of course it's supervised learning, my uncle was there holding me, or my father was telling me what to do, and so on and so forth, right? At best, what did they tell you? Hey, look out, don't fall down, right? So that doesn't count as supervision, right? So, or keep your body right, keep your body up, or some kind of very vague instructions was what they're giving you, right? Supervised learning would mean that, so you get on the cycle, somebody tells you, okay, now push down with your left foot with 3 pounds of pressure, right? And move your center of gravity 3 degrees to the right, right? So this is, so somebody has to give you exactly what is the control signals that you have to give to your body in order for you to cycle, right? Then that would be supervised learning, right? If somebody actually gives you supervision at that scale, you would probably have never learned to cycle, if you think about it, right? Because it's such a complex dynamical system. If somebody gives you control at that level, like gives you input at that level, you'll never learn to cycle. And so immediately people flip and say that it was unsupervised learning, right? Because yeah, of course, nobody told me how to cycle, therefore it is unsupervised learning. So if it is truly unsupervised learning, what should have happened is, you should have watched hundreds of videos of people cycling, figured out what is the pattern of cycling that they do, okay, and get on a cycle and reproduce it, right? So that is essentially what unsupervised learning would be. You just have a lot of data, right, and based on the data you figure out what the patterns are, and then you try to execute those patterns. That doesn't work, right? You can watch hours and hours of somebody playing flight simulator, you can't go and fly a plane, right? So you have to get on the cycle yourself, and you have to try things yourself, right? So that's the crux here, right? So it's how do you learn to cycle is neither of the above, right? It's neither supervised nor unsupervised. It's a different paradigm, right? So the reason I always start out my talks, not just in the class, but in general when I talk about reinforcement learning, is because people always talk about reinforcement learning as unsupervised learning, right? Which always really irks me, because it's not unsupervised learning. Just because you don't have a classification error or a class label doesn't make it unsupervised learning. It's a completely different form of learning. And so reinforcement learning is essentially this mathematical formalism for this trial and error kind of learning, right? So how do you learn from this kind of minimal feedback? Falling down hurts, or somebody, your mom or somebody stands there and claps when you finally manage to get on the cycle. That's kind of a positive reinforcement. Where you fall down, you get hurt, right? That's kind of a negative feedback. How do you just use this kinds of minimal feedback and you learn to cycle? So this is essentially the crux of what reinforcement learning is about, trial and error, right? So the goal here is to learn about a system through interacting with the system, right? It's not something that is done completely offline. Okay, you have some notion of interaction with the system, okay, and you learn about the system through that interaction. Reinforcement learning originally was inspired by behavioral psychology, right? So one of the earliest reinforcement systems that was studied was the Pavlov's dog. How many of you know of the Pavlov's dog experiment? What is the Pavlov's dog experiment?
And Pavlov, he tried to give food to dog, and whenever he gave food to dog, it started salivating. And he rang a bell in association with whenever he is going to give food to dog.
Okay.
So whenever he just started ringing the bell, the dog started expecting the food and it started salivating.
So that is called a conditioned reflex. So when the dog looks at the food and it starts salivating, right, it's a primary response because there is a reason for it to salivate on the sight of food. Any idea why? Exactly. So it's preparing to digest the food. Show the food, it's preparing to digest the food, so it starts salivating, right? So if you think about it, right, hearing the bell and it salivates, what is it doing? Preparing to digest the bell? No, right? So when you ring the bell and then serve the food, the dog forms an association between the bell and the food, right? And later on, when you just ring the bell without even serving the food, the dog starts salivating in response to digesting the food that it expects to be delivered, right? So it essentially, the food is the payoff, the food is like a reward for it, and it has learned to form associations between signals, in this case which was the bell, like an input signal which was the bell, and the reward that it is going to get, right? So this was called behavioral conditioning, right? And so inspired by these kinds of experiments and more complex behavioral experiments on animals, people started to come up with different theories to explain how learning proceeds, right? In fact, some of the earlier reinforcement learning papers appeared in behavioral psychology journals, right? The earliest paper by Sutton and Bartow appeared in Brain and Behavioral Sciences journal. Just go back. I need to say something about Sutton and Bartow. Now that there's a larger audience, we can tell that about them. So we're going to follow a textbook written by Rich Sutton and Andy Bartow, right? But more importantly, they are also kind of the co-founders of the modern field of reinforcement learning, right? So in 1983, they wrote a paper, adaptive neuron-like element that learn control behavior or something to that effect, right? And that essentially kick-started this whole modern field of reinforcement learning. So the concept of reinforcement learning, like I said, goes back to Pavlov and earlier, right? People have been talking about this kind of behavioral conditioning and learning and stuff. But the whole modern computational techniques that people use in reinforcement learning were started by Sutton and Bartow, right? So what is reinforcement learning, right? So it's learning about stimuli, right? The inputs that are coming to you and the actions that you can take in response to it, right? Learning about the stimuli only from rewards and punishments, okay? So you're not going to get anything else. Food is a reward, right? Falling down and scraping your hand is a punishment, right? So only from these kinds of rewards and punishments alone, right? There is no detailed supervision available. Nobody tells you what is the response that you should give to a specific input, right? Suppose you are playing a game, there are multiple ways in which you can learn to play a game, right? So you can learn to play chess by looking at a board position, right? And then looking at a table, right? That tells you for this board position, this is the move you have to make, right? And then you go and make the move, right? So that is a kind of supervision that you could get, that gives you a kind of a mapping from the input to the output, right? That gives you a mapping from the input to the output, and essentially you learn to generalize from that. So this is what we mean by detailed supervision. So another way of learning to play chess is you have an opponent, you sit in front of him, and you just make a sequence of moves. At the end of the move, you win, okay, you get a reward, right? Somebody pays you, say, 10 rupees. Okay, if you lose, you have to pay the opponent 10 rupees. That's all that happens, right? That's all the feedback you're going to get, right? Whether you're going to get the 10 rupees or going to lose the 10 rupees at the end of the game. So nobody tells you, given this position, this is the move you should have made, right? That's what we mean by saying learning from rewards and punishments in the absence of detailed supervision. Okay, is that clear? Okay, and the crucial component to this is trial and error learning, because since I don't know what is the right thing to do given an input, right, I need to try multiple things to see what the outcome will be, right? I need to try different things to see if I'm going to get the reward or not, right? If I don't try different things, right, I'm not going to be able to learn anything at all, right? So I can give you more formal mathematical reasons for why we need all of this as we go on, but intuitively you can understand this as requiring exploration so that you know what the right outcome is, right? And there are a bunch of things which are also characteristic of reinforcement learning problems. One of those is that the outcomes, right, the rewards and punishments based on which you are learning can be fairly delayed in time. They need not be temporally close to the thing that caused it. I mean, while you are playing a game, let us say, right, so you might drop a batsman, right, and then he goes on to score like 150 or something like that, right? So then you lose the match at the end of the day, right? But the event that caused you to lose the match is the dropped catch that probably happened around the 12th over, right? Or it could be a much more convoluted cause and effect, right? So, and how many of you follow cricket? My God, really losing popularity, yeah? Put your hands down. I'm not going to give a cricket example then. Look at it. Okay, so there are a bunch of other things, right? So we talked about delayed rewards. The rewards could come much later in time from the action that caused the reward to happen, right? For example, let's go back to our cycling case, right? I might have done something stupid or I might have gone over a stone somewhere, right? While I'm cycling at a very high speed, there might have been a small stone in the road, and that will cause me to lose my balance, right? And then I'll try my level best to get the balance back, right? I might not, and I'll finally fall down and get hurt. That doesn't mean what caused the falling down is the last action I tried, right? I might have desperately tried to jump off the cycle or something like that, but that is not what caused the punishment, right? What caused the punishment happened a few seconds ago when I ran over the stone, right? So there could be this kind of a temporal disconnect between what causes the reward or punishment from the actual reward and punishment. So it becomes a little tricky how you are going to learn those things, right? Learn the associations, right? So quite often, right, you are going to need a sequence of actions to obtain a reward, right? It's not going to be like a one-shot thing, right? You're going to need a sequence of actions to get to the reward. So again, going back to the chess example, right, you are not going to get a reward every time you move a piece on the board, right? You have to finish playing the game. At the end of the game, if you actually manage to win, you get a reward. So it's a sequence of actions, right? And therefore, you need to learn some kind of an association between the inputs that you are seeing. In this case, it will be board positions, right, or how fast the cycle is moving and how unbalanced do you feel and so on and so forth, right? Two actions. So the inputs that you are getting, which sometimes which we will call states, right, and the actions that you take in response to this input that you are seeing, right? So this is essentially what you are going to be doing when you are solving a reinforcement learning problem. So this kind of associations are essentially known as policies, right? So what you are essentially learning is a policy to behave in a world, right? So you're learning a policy to play chess, or you're learning a policy to cycle, right? So this is essentially what you're learning, that you're not just learning about individual actions, right? And all of this happen typically in a noisy stochastic world, okay? That makes things more challenging. So these are all the different characteristics of reinforcement learning problems. So reinforcement learning has been used fairly successfully in a wide variety of applications, right? So you can see a helicopter there, okay. So that's not a cut and paste error. Okay, the helicopter is actually flying upside down. Okay, so this group at Stanford and Berkeley, which have actually used reinforcement learning to train a helicopter to fly. All kinds of things, not just upside down. An RL agent can do all kinds of tricks on the helicopter. So I'll show you a video in a minute. It's an amazing piece of work, right? I mean, it's considered. It was considered the showpiece application for reinforcement learning. I mean, getting such a complex control system to work, and it actually could do things at a much finer levels of control than a human being could. Right? I mean, that's after all a machine, so you would expect that. But the tricky part was how it learned to control this complex system without any human intervention, right? And in the middle, right? So I have a couple of games there. So that is. Can you see that? Okay, it's too small an arrow. Yeah, that's a game called backgammon, right? So how many of you know about backgammon? 1, 2. There was one maybe. How many of you know about Ludo? Okay. You're sleeping? Oh, okay. Okay, fine. So backgammon is like a 2-player Ludo, okay? So you throw the dice, you move pieces around, and you take them off the board, right? So it's a fairly easy game, but then you have all kinds of strategies that you could do with it. But it's also a hard game for computers to play because of the stochasticity, right? And also because of a large branching factor that is there in the game, right? So at each point there are many combinations in which you could move the board pieces around, and then there is this die roll that adds an additional complexity. So people weren't really getting great results. And then there's this person Jerry Tesaro from IBM who came up with something called Neurogammon. I think it was called Neurogammon, and that was trained using supervised learning and a neural network, right? And so if he had done it recently, it would have been called a deep learning version of Neurogammon or something, because he did it back in the 90s, early 90s. It was just called neural network version of backgammon, and it played really well for a computer program, right? So it was essentially the best computer program backgammon player at that point. And then Jerry heard about heard about reinforcement learning, and he decided to train a reinforcement learning agent to play backgammon. Okay. So what he did was set up this reinforcement learning agent which played against another copy of itself, right? And let them play hundreds and hundreds of games, right? Rather thousands and thousands of games. So essentially what they did was, so you train one copy for like 100 games or something, then you move it here, right, freeze it, and then continue learning with this. So essentially what was happening, as you learn, you are playing against better and better players. Gradually your opponent was also improving, right? And then so this was called self-play, right? So he trained backgammon using self-play, and it came to a point where the TD gammon, as he called it, was even better than the human player of backgammon at that point in the world, right? So they actually had a head-to-head challenge with the human champion. There is a world championship of backgammon, it's apparently very popular in the Middle East, and people actually have world championships. That's a world championship of backgammon, and so he challenged the human champion, which IBM seems to do a lot, right? I mean, they challenge Kasparov to matches and things like this. So he also challenged. This sort of worked for IBM. You should realize, right? People who spend a lot of resources getting computers to play games will probably be working for IBM. So Jerry had this thing, and it beat the world champion. So we have reinforcement learning agent. That's the best backgammon player in the world. Okay, not no more best computer player or anything. Right? So we could actually make that claim, right? And there's another game there, which is a snapshot from the game of Go. Right? So people have played Go. Oh, come on, usually there's at least 1 or 2 people who have played Go. Okay. People have played Othello. Okay. That's also a very few number. I mean, isn't it one of those free games on Ubuntu? I thought everybody plays that because I mean at some point or other, well, you would rather play Othello than watch paint dry, you know. But anyway, so Go is like a more complex version of Othello, if you will, right? It's again a very hard game for computers to play because the branching factor is huge, right? And it is actually a miracle that humans even play this because the search trees and other things are really complex, right? So this is one case which clearly illustrates that humans actually solve problems in a fundamentally different way than we try to write down in our algorithms, because we seem to be making all kinds of intuitive leaps in order to be able to play Go, right? So there's this person, David Silver, who currently works for Google DeepMind, and but before that he spent some time with Jerry Tesaro at IBM, and at some point along the way he came up with this reinforcement learning agent called TD Search that plays Go at a decent level. It's still not not like master human level performance, but it plays at a pretty decent level. Right? So what I'm pointing out here is things that are typically hard for traditional computer algorithms or even traditional machine learning approaches to solve. AI has had good success, right? And here is another example. Oh, if I'm to point, I'm supposed to use this or that. I forget which one. Right? They have told me I should use only one of those screens for pointing because it's hard for them to record on the other one. I forget which one. Okay, forget it. There are some robots on the bottom left of the screen, right? And so that's a snapshot from the UT Austin Robo Soccer team called Austin Villa, right? And they use reinforcement learning to get their robots to execute really complex strategies. So it's really cool. But the nice thing about the Robo Soccer application is that they don't use reinforcement learning alone, right? They actually use a mix of different learning strategies and also planning and so on and so forth, which is going on in the other studio, right? So they use a mix of different kinds of AI and machine learning techniques in order to get a very, very competent agent. It's very hard to beat, and they have been the champions, I think, for like 2 or 3 years running now in the humanoid league, right? And again, hard control problems. Things like how do I take a spot kick? Those are the things for which they use reinforcement learning, which are really hard balancing problems. You basically have to balance the robot on one leg and then swing the other leg so that you can take the kick. And it turns out to be a hard control problem, right? So they used RL to solve those, right? And then up on the top right, okay, is an application which will probably the one that actually makes money of all these three, all the others, right? That is on essentially on using reinforcement learning to solve online learning, right? So online learning is a use case where I don't have the feedback available to me a priori, right? So the feedback keeps coming piecemeal, right? So for example, that is a case where we are having news stories that need to be shown to people that come to my web page, right? And when people come to the page, I'll have like some editors will pick like 20 stories for me, and from those 20 stories I have to figure out which are the ones I put up there prominently, right? And what is the feedback I'm going to get? Nobody tells me what stories that user is going to like. I mean, I cannot have a supervised learning algorithm here, right? So the feedback I'm going to get is if the user clicks on the story, I'm going to get a reward. If the user does not click on the story, I will not get a reward. Right? That's essentially the feedback I'm going to get. Nobody tells me anything beforehand. Right? So I have to try out things. I have to show different stories to figure out which one he's going to click on. Right? And I have very few attempts to do this in. So how do I do this more effectively? So people have done a supervised approach for solving this, and it has worked fairly successfully. So it has worked fairly successfully, but reinforcement learning seems to be a much more natural way of modeling these problems. So not only in this kinds of news story selection, people use reinforcement learning ideas even in ad selection. Right. So how do you see some of those ads that you see on the sides when you go to Google or some other page, right? So how are those ads selected? So there might be some very basic economic criterion for selecting a slate of ads. Okay, here are these 10 ads which would probably give me the right payoff, right? And then you can figure out which 3 of those 10 am I going to put here, and things like that. You could use a reinforcement learning solution for selecting those, right? Of course, there is this whole field called computational advertising, right? It's a lot more complex than what I explained, but RL is a component in computational advertising as well, right? Okay, here is the video courtesy Andrew's web page. The people recognize the guy there? Yeah. Huh. Okay. It's not a human-sized helicopter, but still, it's a fairly large. Amazing, huh? All of this is being learned by a RL agent. So this goes on for a while, so we'll stop.